Good afternoon, sir. Thank you for accepting our invitation, sir. Now I request Mr. Ramnishant, sir, to introduce our speaker to participants.
Good afternoon. I'm Ramnishant from Department of ECE, Gayatri Vidya Parishad College of Degree and PG courses. And I would like to introduce Professor Hardik Pandya. Professor Hardik Pandya joined the Department of Electronic Systems Engineering, Division of EECS, Indian Institute of Science, Bangalore, in January 2017. Dr. Pandya heads 3 laboratories in ESC focused on developing a new class of biomedical devices and technologies. Before joining the Indian Institute of Science, he worked as a postdoctoral scientist in the Department of Mechanical Engineering, Maryland Robotics Center, University of Maryland, College Park, from 2012 to 2016, and in the Department of Medicine, Brigham and Women's Hospital, Harvard Medical School, from 2016 to 2017. He obtained his PhD in microelectronics technology from the Indian Institute of Technology, Delhi, in 2013. His current research focuses on minimally invasive and non-invasive technologies with an emphasis on, but not limited to, cancer diagnosis, brain, breast, head, and neck, as well as eNOS on diabetes, breast cancer screening, neuroprotective therapies for acute stroke and epilepsy. He is a recipient of the prestigious Early Career Research Award from Science and Engineering Research Board, Government of India, in 2017. His group consisting of 24 research scholars, out of them 2 are postdoctoral fellows, 10 PhD students, 4 MTech students, and 8 project assistants, is actively working with 20 clinicians on several projects in the medical domain. His work has resulted in 11 patents, 2 book chapters, and around 50 publications in peer-reviewed journals and conferences, while his recent work on developing a wearable device for measuring SpO2 and temperature for COVID-19 was highlighted in the Hindu newspaper. His work has also been highlighted as breaking research news by the Physicians Committee for Responsible Medicine. The work on portable cancer diagnosis tool was also featured on Science Translational Medicine as an editorial choice, breast cancer diagnosis, March 2016, and has been highlighted on K-Pray blog as biochips and diagnostic tools in April 2016. Dr. Pandya is also serving as a non-executive director, technical advisor to 2 Indian medtech companies. Thank you very much, Dr. Pandya.
Yeah, thank you so much. So let me know when I can start.
Yes, you can start now, sir.
Yeah. So good noon, everyone. May I request all of you to just mute your mic so that it will not be a disturbance for all of you when I speak. That will be easy. And what we will do is I'll be discussing about the smart sensors, right? And I'll be talking for about 50 minutes, followed by 10 minutes of interactive session, where you are free to ask me anything and everything that you can ask from the technical domain and other related stuff. So once again, thank you for having me today on this particular occasion. Let me share my screen. Okay, so I hope everyone can see the screen. Just one of you can tell me if you can see the screen or not. Oh, great. Okay, thanks. So yeah, as the topic suggests, we will talk about smart sensors. And first, when we talk about sensors, we know that human body itself has millions of sensors, right? If you take just a nose itself has trillions of sensors, right? And it is connected with a brain, and that's how we call it a neural network, right? When it is a network of neurons processing the signal, and the signal comes out of the sensors, and that's why together it is called a electronic nose if we fabricate sensors in-house and connect it with artificial intelligence. This is just one example, but when I'm talking, you are able to hear, right? So there is an audio sensor. When I'm talking, there's a speech, right? So there's a and then you can see. So you have a visual sensor. You can feel it. You have a haptic sensor. You can press and feel something. You have a force sensor. So there are millions and millions of sensors within human body, and we are talking about smart sensors, but our body itself is extremely smart. We never thought about the sensors from our body perspective, right? So anyway, the point is, before I start the going into details, I have selected 2 or 3 topics that we will be discussing for today as well as tomorrow. But before I go into depth, let me just give you a bit of details of what we do at IISc. So as you can see the slide, I have 2 laboratories here. The third one is of course a computational laboratory where we fabricate the microsystems and transducers and biomedical devices in one of the fab labs that we have within my department. It is a class 1000 clean room environment. And then we have another laboratory on the 2nd floor. If you visit sometime to ISC and to my department, I'll show it to you, which is focused on characterization of the sensors, which is called Biomedical Electronic Engineering Systems Laboratory. The -6 to -9 stands for micro to nano. And in short, we call it a bees lab. It's nothing to do with the bee that you see in the screen. Of course, that is my work, but don't get confused by that. If a bees lab, we work on bees. Okay. So, of course, my name is very easy to remember for most of you who like cricket, right? It's like the name of a cricketer, Hardik Pandya. So let me start with a little bit about myself, and then I'll tell you that why I am a right person to talk about sensors at least, right? There are a lot of scientists working with your engineering college or in your engineering college who are good in many stuff. I personally feel that I am okay on fabricating sensors, microsystems, and healthcare technologies. And the reason I feel confident is because I have been trained in this domain from last 12 years. I got my PhD from IIT Delhi. I was a postdoc at Maryland and postdoc at Harvard Medical School, right? And right now, from last 3.5 years, I am a professor here at DESE, which stands for Department of Electronic System Engineering. Earlier, it was called CEDT, and I'm also associate faculty to CPDM, which is Center for Product Design and Manufacturing. Having said that, rather than going into much details about the number of patents and this and that, let me come to the collaborators, which is very important stuff. See, if you talk about smart sensors, and if you want to talk about healthcare technologies, or use your electronic systems and design or engineering into healthcare, it is very, very important that you have a right set of collaborators. And when I say right set of collaborators, means clinicians on board is very, very important. They are the people who will give you an actual problem that they face in their daily routine, right? For example, we have a set of neurosurgeons. We have Sabri, Vikas, Manish and Lingaraju. Vikas, Manish and Lingaraju, they are all from Demens, while Shabri is from Ramaya Institute, Ramaya Hospital. Anita is a neuropathologist. She's a professor as well. Now we have cardiologists, a group of cardiologists. If you see, we have Prasanna Sima from Jaydeva. We also have Deepak, who is an electrophysiologist, again from Jaydeva. Then we talk about ENT, right? Say we have Manjunath from who is from Hubli, right? He is ENT surgeon. And if you talk about neonatology and pediatrics, then we have Sanjay, who is a pediatric surgeon. We have Niranjan and Pratik, who are neonatologists. Talk about physiology, like EEG, right? So we want another collaborator. So we have Mahesh and we have Latika. Latika is from AIMS Rishikesh. We have oncologists, group of oncologists. You can see Moni Abraham. Moni Abraham is the director of Cochin Cancer Research Institute. We have Subramaniam Iyer, who heads the head and neck oncology at Amrita Institute. Gayatri Gogoi is from Assam Medical College. Vishnu Kurpad is from is a breast cancer surgeon from Shankara Hospital. We have Sunal Asthana, who is a liver transplant surgeon. We have Narayan Subramaniam, who is a head and neck oncology from Majumdar Shaw Medical Foundation. We have Satish from Oxford. We have Jayant Vaidya, who is a breast cancer surgeon and professor at University College London. So these people actually are the ones who collaborate with us, right, and give us the right problems that we have to work on. It's very important, right? Sitting in the lab, sitting in the office, you cannot find a healthcare and biomedical kind of problems, right? So I'm very indebted with all these collaborators, excellent human beings. You meet them, you will feel that they are really curious in doing research. Okay, having said that, it doesn't mean that you should not have academic collaborators, right? And when I say collaborators, does not, you don't have to go too far. You can find collaborators within your institute as well. So these are some of the collaborators from my institute and from abroad. Rather than going into details, I'll just say that from neuroscience and AST, I have few here. I have Sachin, and then I have Chetan here. Also, I have Rishikesh Narayan from MBU. And in biological sciences, I have Nagasoma. This is Annapurni Rangarajan, then Deepak, Professor Balaji, and Deepsika Chakrabarti. In systems, Manoj is there, and then here, if you say internship collaborator, Jaydev Desai was my postdoctoral supervisor at Maryland. Now he's at Georgia Tech. I have Yongjin Kim, and Yongjin is a professor in South Korea. Ida is in Penn State. Then we have few people from MITs. We have Jayant, again, like I said, from UCL, right? And then we have a few people from Stanford Medicine. Here is Sanjeev. He is in Stanford Medicine. And then we have a professor from Manchester, right? Sarah Cartwell, who is here. So the point that I'm making, we also have Kai and we have Rangathan. So anyway, the point that I'm making is that along with having a good clinical collaborators, it is also important to have academic collaborators. Now, that does not mean that you should start giving your PhD students to them, okay? It is just to understand that how we can collaborate on complementary research field. So very important. So today we will be talking about smart sensors, and these are few of the sensors that I am showing you to here. We'll go into details of few, right? And when you talk about healthcare technologies, most of the people feel that healthcare technology is like taking 2-3 things together and joining it. It's not like that. It's an area where you require expertise in analog electronics, you require expertise in microengineering, you require expertise in machine learning, embedded systems, electronic system design, and of course you should understand human physiology. So it's a combination of many things into one. Of course, I have not written here additive manufacturing or subtractive manufacturing is an important part of developing the product. So we will not go into details of all this, but we will go into details of few of those. So let me just give you an example of few, and then we'll go in details of few projects. Okay. So the first one is an intubation catheter integrated with MEMS-based sensors. Now, don't get too much overwhelmed with the words that I will be using. It's very simple. Intubation catheter is something that you can intubate. You can put within the trachea. Trachea is nothing but a windpipe. Now, what is the problem? The problem here is that, and we'll discuss this thing in detail also, that when the babies are on the ventilator, their windpipe starts inflating. So the windpipe, which is also called in technical terms trachea, is get inflamed, then it's difficult to breathe, and in most of the cases the patient dies. So the point is there is no catheter right now existing in medical domain which can in real time tell that the trachea is inflamed. So we are trying to make a catheter. Catheter is nothing but a tube which is biocompatible, and this catheter is integrated with flow sensor array. It is integrated with chip memory alloy. Chip memory alloy is SMA. It's made up of nitinol. It's two different materials, and that's why it's called alloy. Two different metals, when you fuse, it becomes alloy. Then we have a tactile or haptic sensor at the tip of the catheter, and you can maneuver the catheter with same memory alloy. We'll go into discussion in few slides. Now, these are some of the micro needles that we have fabricated. This is for neural stimulation. So, you all understand EEG, right? ECG, EEG, and EMG. When you talk about ECG, it is electrocardiography, right? When you talk about EEG, it's electroencephalogram. Talk about EMG, electromyogram. But when you take the signals from the brain, now when you place it on the forehead, doesn't mean the signals are not coming from the brain. It is coming from the brain, but there is an impedance that is there because of the skull and skin and tissue and other things. Finally, on the scalp, on the forehead, when you put the electrodes, you will measure EEG. But if you open the skull and directly place the electrode or implant the electrode on the brain, it becomes ECOG. And ECOG stands for electrocardiography. Okay, so that is something which is very interesting and important to understand, particularly when we talk about epilepsy. And when we talk about epilepsy, it is nothing but fit. So to understand the epilepsy and the signals generating from the brain, right, it's very important that we have a needle that can be placed inside the brain, right, and you can measure the signals coming from different layers of the cortical column. So the group of cortical columns makes a cortex. And when you place the needle inside the cortex, you can get the signals from each cortical column. Each cortical column is divided into different layers, layer 1 to layer 6, and we are understanding the signals coming from different layers of the brain. Anyway, the point here is that we can fabricate micro needles. As you can see here, it is over 1 cent, and you can see here it's almost similar to Lincoln nose. So the represented diagram is to show that the device itself is extremely small or tiny, or you can say micro. Now, when you talk about micro, it's very important that to understand what is micro. Micro, of course, everybody knows it's -6, right? So it is equivalent to a human hair. Human hair is about 80 to 100 micron thick. 80 to 100 micron, depending on from where we are. If you're from Kerala, you have a thicker hair compared to if you're from different state. Reason is nutrition. Reason is oil. Reason is the living, the way people eat, consume food. A lot of reasons are there. The point that I'm making is that a thicker hair you will find at certain places compared to thinner hair. However, the variation is only 20 microns. So it is 80 to 100 microns is the thickness of a human hair. We are talking about few tenths of microns. So that means that we are really talking about micro systems. Now, let me go to another platform again. This will discuss in detail in the coming slides. However, this is just to give you some understanding about what kind of sensors you can design and what kind of applications you can think of if you have those sensors. So this is a microchip that you can see here. The sensing layer is exactly in the center of this chip here. And this sensor has micro heater, it has interdigital electrodes, and it has 3 thermistors on the sides. We will discuss this. This is a PCB that can be used to attach this particular sensor, which you can see here, right? And then we have created an entire system that can be used to understand the change in the tissue property. All right, we'll talk about which kind of tissue, how it can be used for measuring those changes. Let me go to the next slide. This is about bioresorbable sensors or sensors of future. You can say smart sensors, right? Here, what we have designed is a chip or a microchip, right? That can be used to understand the signals generating from the surface of the brain. Now, you don't have to really implant or indent the brain tissue. You open the skull and you place the chip on the brain, and you will measure the ECOG signal. When you close the skull, suture the skull, and you measure outside the head, it is EEG, right? ECOG, EEG. This is ECOG signal, or you can say IEEG. But the point is that we can use this particular chip. It can be implanted on the rat's brain, and you can measure the change in the signal coming from the ECOG. If there is an epilepsy, you can immediately measure there is epilepsy. And if you want to understand the efficacy of a drug, efficacy is nothing but efficiency of a drug. Then you can load the drug from the central hole. Here you can see that white color central hole onto the brain of a rat. What will happen is, if the drug is effective, the drug efficacy is great, then all the seizures will stop and you will get the normal brain signals. If the anti-epileptic drugs are not great, you will see continuing of the seizures in this particular case. Epilepsy, again, you can divide into multiple types. Our idea is just to understand the efficacy of a drug. So that's why the one important thing about this particular chip is once you implant in the brain, after 21 days it gets dissolved in the brain, dissolved or absorbed or resorbed in the human body or on an animal body. So the advantage is that you don't have to reoperate the patient, right? So that's why we say that we are working on this particular chip is a sensor of future, because we have to do a significant amount of work to be utilized inside the human brain. Okay, let us move to next topic. Let me assure you that I'll go into discussion in detail about most of them, right? In few minutes. This is just to give you a glimpse of how you can use the sensors for different application. This you can see here. This is a micro force sensor, and you can see 4 bridges here, right? And each bridge has a micro what you call piezoresistor. Here there is a piezoresistor. Then here there is a piezoresistor where the bridge is connecting to the circle. Okay, this line has a piezoresistor. Same way here there is a piezoresistor. Same way here there is a piezoresistor. So that means you have about 4 piezoresistor, and then you have 4 more to balance the bridge out. Okay, so the point here is that how can you fabricate this particular micro force sensor? And first of all, why we should fabricate micro force sensor, isn't it? So this is used for atrial fibrillation. Now, what is atrial fibrillation? Generally, if you see the human heart's beats 60, 65, 70 beats a minute. In some cases, the heart beats extremely fast. That is called arrhythmia. In few cases, the heart starts pumping unevenly, fast, slow, normal. That is called atrial fibrillation. Okay, so the lot of subjects or heart patients, they go for AFib, or they have AFib, which is atrial fibrillation. And the difficulty is that because of the uneven beating of heart, there is a possibility of developing a clot, and that clot can cause heart disease or heart attack. Now, the way to cure is to insert the catheter and to burn that area. The burning is called ablation. We'll go into detail. But the point here is that there are no catheters which can give the feeling to the feeling of force to the clinician. That means that if a surgeon is operating the patient, he will insert or she will insert the catheter inside the human body, right? Reach to the heart, apply a force. They can see the force, but they cannot feel the force. Now, if you feel the force, how much you are applying, the surgery will become better. That feeling of force is called haptics. So can you have haptic feedback to the catheter so that the overall surgery becomes better? For that, we are designing a force sensor. And in fact, an entire catheter, as you can see here, we are using the pig's heart, because pig's heart is much more closer to human heart to test the performance of this particular catheter. So let me go to the next slide. Now, this is a slide where you can see that there is a system, right? There is a system here, and this system has a different LED and a detector. These 3 LEDs are all in the NIR range, more or less. You can see from 850 nanometer to 935 nanometer to 1060 nanometer, and then there is a OPT 101, which is a photo detector. It will just measure the transmission of the IR through the tissue. The tissue is placed in the center of this particular stage, and the idea here is to understand what is the change in the NIR value when you use a normal tissue and when you use a cancerous tissue. Can NIR be used as a modality to differentiate or to delineate cancer from normal in case of breast cancer? Right, that is the idea. This is a system design. We have published around 2 papers on this particular work and publishing more. So let me go to the next slide. This is on oral cancer. Again, I'll not be discussing this particular slide in detail because the topic is on smart sensors. However, this is a smart system, not just smart sensor, but the entire system is smart. Why? Because, okay, let us understand oral cancer. Oral cancer is a cancer that occurs in the mouth, right? There are different reasons of having oral cancer. The first study is a brush biopsy, where a brush is used to take the cells, and the cells are stored in a vial, which is sent to a tertiary clinic, where the oncopathologist or pathologist will smear the cells on the glass slide. Smearing is to spread the cells on the glass slide and stain it with H&E staining and look at the morphology of each cell. Okay, morphology means shape, size, nucleus, double nucleation. Now, if the cancer is there in the cell, it will look different compared to normal cells. But the reason, the advice would be atypical. The pathologist will not say it is cancer or which grade. The report will come only as atypical. Atypical means a person has to go for histology. Okay, study of cells, cytology, study of tissue, histology. So a person has to go for histology where the tissue is taken out, and then they understand by slicing the tissue using different biomarker whether there is cancer or not. You understand? So now you are looking at cytology, study of cells. If the results are atypical, if the cell morphology is different, and the person has to go for histology. The difficulty in the first case, which is a cytology study, is that the pathologist would miss pre-malignant cases, pre-cancerous cases, where the morphology is changing, but it is difficult to look under the microscope with human eye. Right? It's very difficult, and that's why you can see the sensitivity value for HGD versus LGD, which is high-grade dysplasia versus low-grade dysplasia, is only 25% when it is done by manual method, but it reaches to 73% when it is done by risk stratification, or you can say a combination of image processing and machine learning. Okay, so the advantage of developing this particular microscope is one, that you smear the glass slide like you get the cells, right? You smear the glass slides, stain with H&E or stain H&E, and then smear the glass cells on the glass slide. Load the glass slide on the microscope, press a button. That's it. When you press a button, it will scan entire slide, take the images of each cell, process it, differentiate the cells from the noise, that means the bacteria, some other particles. It will identify which are cells in the glass slide. Look at the cells, because the neural network is trained with the normal cells, with the cancerous cells. It will only send the cells to a remote pathologist, or if the system is right in the pathologist next to pathologist, it will show the cells which are atypical to the pathologist. That means that we can improve the pre-malignant screening by using this system. System not only is able to quickly identify which cells looks atypical, but will also identify pre-malignant cells which were missed by the pathologist. Thus, I say that it is not just a smart sensor, it's entirely a smart system. We call this a Amura. Amura comes from the word Amur, which in Sanskrit means intelligent. Okay. Let me go to the microsystem and healthcare technologies. So we work on non-communicable diseases. We work on communicable diseases. When you say about non-communicable and communicable diseases, it's very easy to identify. For example, COVID is a communicable because it can infect person to person, right? While if you say cancer generally is not non-communicable disease. So we work mostly on non-communicable disease. We work on communicable diseases such as antibiotic susceptibility, or you can say the bacterial infections. But what we work is we make a system, we make a devices, we make sensors, and understand the problems that occurs in a heart or in a breast cancer or tracheal inflammation or oral cancer or neonatal hearing or even brain cancer. And when it comes to tools, so we develop protein-protein interaction tool, we develop a drug delivery tool, we have developed antibiotic susceptibility tools, we have developed surgical tools, and of course cytology I just shown it to you in the last slide. Okay. Now coming to the lab. So to do all the things you require a facility, right? So in last few years, right, with the help of my institute, and of course I got funding from government, right, I was able to raise around 8 crore to establish all these facilities that I'm talking about. But of course, when you talk about this amount, it looks like because somebody is working in IISc and that's why the person gets money. It is not a correct statement. If you see the proposal that I write, right, and I'm happy to share with one of your professors, you will clearly see why or how much is the difference in the proposal quality. Now, I'm not demeaning any other professors from any other universities. My only point is that the proposal quality should be extremely important. And if you learn how to write a proposal in a right way, the funding can come to any institute. Okay, nobody is against anyone when it comes to reviewing the proposals in DST, DBT, DRDO. Right, we all look at the proposal with the same eyes. Okay, there is no bias here. So you will clearly see the difference. When we write a proposal, we don't only write what we want to do, we also write what prototype we have made. We also show the preliminary results. We have a clearance. We have the possible resources to work on the proposals. So it's a different game. Anyways, having said that, it does not mean that the proposal coming from other universities are bad. It is great, but how we can improve it further so that there is a short chance of getting funding, that is another thing that we can discuss at some point of time, probably with the faculty of your university. Okay, having said that, let me show you some of the facilities that we have here in the department, and that is my laboratory. This left side that you see is a thermal evaporation or E-beam evaporation. The next slide that you see is about wet benches, acids and solvent. The next slide you see is a yellow room where there is a fume hood, and then we have got one more system which is a photolithography system of about a crore. This is a system that will come in the clean room. We have it ready to be installed in a few days. This is a stereotaxic equipment. This is to hold the red and to insert the sensor into it. There is plasma bonding. It is used for bonding the PDMS with glass or microfluidic devices. This is about spin coater. It is for photoresist coating. Now, these are some of the other part of the lab in the second floor. We have metallurgical microscopes, and then we have biostatic pumps, which is shown here. Of course, desiccators and oven and this and that, which you already have in your place, right? We have biosafety hood too. This is very important because when you work on communicable diseases, particularly bacteria, right, and then too like E. coli, then you can use BSL2. However, if you want to use virus and which are really contagious, then you have to go for BSL3, which is biosafety level 3. This is a micromanipulator. Is used to manipulate the indenter onto a tissue. We'll discuss in detail. Okay, so let me come to the first topic and we will go into detail about this particular topic. So the topic says that we will be talking about electrothermomechanical phenotyping breast cancer tool for better diagnosis of breast cancer. Now, this work is done by my student Anil Vishnu. Any work that I am showing it to you here, the credit goes to my students, right? I just guide them, right? All the work is done by students. Okay, so if you like something, it is all because of the student work. Okay, so let me start with the breast cancer health burden. As most of you already know, breast cancer is the second largest cause of death, cancer-related death in women. Okay, and it's about 14% of all the cases. While if you see the number of new cases also is increasing and it's about 27.7%. It's a really very big number. Okay, now the important thing to note here is that even though the incidence level of the breast cancer is extremely high, the mortality level is comparatively low compared to lung, colorectal, prostate or stomach. Okay, so at stage 1, if you identify a patient, 95% is a chance of survival. At stage 4, it becomes 18%. The another thing that is very important, that if it is breast cancer is second largest cause of death, cancer-related death in women, same thing goes for prostate cancer for men. Right, most of us who lives longer, right, about 90, would probably have a prostate cancer. So it's very important to understand all these things in detail. Now, first question is, that what is a breast anatomy. Now, breast anatomy, when you understand, so there is a duct, right, from which the milk comes. All of us are blessed to have our good immune system because we were fed milk by our mother, right? So you are surviving in COVID because your immune system is better. So all we should never forget what a woman can do for a man's life, right? You can never repay back. It is equivalent to a goddess, staying with you. If you have mother and father staying with you, and I can tell you from my own experience, I stay with my mother. That's why I'm telling you. Anyway, the point that I'm bringing is that duct is the through which the milk comes. Then there are lobes which are next to the ducts, and then there is a fat like you can see here, and finally there are bacterial muscles which holds the breast. Okay, so 70% of the cancer comes from duct. It's called ductal cancer. Then remaining comes from lobe. It's called lobular cancer. Then it comes from duct and lobe. It's called mixed tumor cancer. Then there is an inflammation either in lobe or in a duct or in some part of the breast. It's called inflammatory cancer. Then there is a mucus. It's called mucinous cancer. So several substage of breast cancer. Okay. Now, let us see a video, and then I will show you two videos so you understand, and then we'll go to the next slide to see why we have to design an electronic system, right? And what is the difficulty right now in this particular area. Let me play the first video. Right. Now let us see about breast cancer as well. Right. So we have seen these two different things, right? One is the anatomy. So if you talk about a particular organ, you need to understand the anatomy of the organ. So you understand further what are the problems, right? And where exactly the problem arises. So the reason of showing you the anatomy, and of course, I completely acknowledge the nucleus media, medical media from which we got this video. It's more like informative video. But the point that I was making is along with understanding we should understand then stages of cancer. Okay. Now, if you see this particular slide, you will understand that, there is several ways of screening a subject. Now, for example, if a patient feels that there is an inflammation, now once in a month, a woman can do a self-examination. Self-breast examination is called SBE. Which is that when in shower she can check about inflammation or mucus or any other symptoms, right, which is not or which is unusual. So if that is the case, a subject or woman should go to clinical breast examination, which is called CBE. So like I said, first is physical examination or history. Second is clinical breast examination, where the doctor will check if there is any problem. If the doctor feels that there looks like an issue, then doctor will suggest to go for mammography or MRI or ultrasound, and followed by blood chemistry studies. If the mammography shows a region which is suspicious, then a person has to go for biopsy, where a tissue is taken out from that particular part of the breast which looks like suspicious. Okay, and tissue is taken out using a needle, so it's a needle biopsy. It's just a cylinder tissue that comes out. When that is done, then they slice the tissue, okay, which is out, so outside the body, ex vivo. Okay, let me tell you three terms. In vivo, within the body; ex vivo, outside the body; in vitro, onto a laboratory platform. Okay, you grow the cells on the lab in vitro. Now, what we are talking about is the tissue is taken out from that region, and it is sliced, and different biomarkers are looked at it. For example, estrogen biomarker, progesterone biomarker, HER2 plus minus biomarkers. These biomarkers are looked at, and then it is diagnosed as a cancer. If yes, what is a stage and what is a subtype? Okay, so this is the complete cycle. Now, where do you think that there is a requirement of us developing or intervene in this particular cycle, right? So there is a cancer called triple negative breast cancer, where all this histopathological analysis, again I told you, right, cytology is study of cell, histology is study of tissue, histopathological analysis is study of tissue analysis. Okay, so there is a triple negative breast cancer where all this histopathological analysis biomarkers are absent. That means a person has cancer, but the result comes as person is okay, right? Which is not great. So that is one thing. Second thing is that how quick you can develop or diagnose whether there is cancer or not in an intraoperative environment. That means when a surgeon is operating a patient, right, the tissue is taken out, it is sent to a pathologist, and the pathologist will give the report. This takes 2 hours. So by the time patient has to be in the surgical room, so our operation theater. So can we develop a system that the tissue is taken out and our system can tell immediately whether still there is cancer or not? Whether it cannot tell substage or not, we don't care when it is surgery. Surgery is removing the tissue, immaterial of the stage. Okay, so that is the idea, that we want to develop a system that can be used inside an operation theater, one, and second is that can be used to identify triple negative breast cancer, which oncopathologist or pathologist misses. So there are two questions that we are addressing. And of course, there is a context and significance when it comes to the prevalent. 27% of the cancers are prevalent. There is a patient burden. About 62% of expenses out of pocket. There are a lot of good government schemes, right, for every state that can be utilized, but still the patient has to pay out of pocket because the expenditure is extremely high. There is a shortage of manpower. We have a less number of clinicians, even lesser number of pathologists. So there's shortage of manpower. If selected in early stage, then there is a 95% survival rate. There is a gaps in existing technology, as I already told you, right? And very important thing that you can see here is 65% of Indian healthcare market is largely dependent on imports, right? And that's why when you see the schemes from government like Atmanirbhar Bharat, or you can see schemes like Make in India, right? There is a reason that we should start developing systems within our country. You will see that a lot of collaboration happens because people wants to use the data from our country, right? They develop something outside and they want to do a large set of study, large cohort of patients. So they come collaborate with some professor and get ethical clearance and then do a large study of 10,000 subjects. Take the data, make the system better, sell it back to us at a very high cost, right? We have to change that mentality. We have to change ourselves. The way to change is if we start involving ourselves on the healthcare, towards the healthcare, using the electronic systems, using the electronics engineering or mechanical engineering or AI or additive manufacturing or product design, anything and everything can be utilized to develop a healthcare ecosystem. When many of us would try, there will be at least few products that will our country, right? For our country people, rather than anybody else developing something for us. Now, it will take time. We not only government, right? It is our duty also to change our mentality and to work hard to participate in this kind of schemes. Okay. So now coming to the last one, which is clinical requirement, there is an importance, there is a difficulty in getting the surgical on the surgical table, like you can see here. I discussed about that, and that's why the research questions that we are addressing is first. Now you understood that there are biomarkers, right? Instead of biomarkers, if I have the tissue, can I measure the electrical property of tissue? That means resistivity or impedance. Can I measure thermal property, the thermal conductivity of tissue? Can I measure mechanical property like elasticity or stiffness of tissue, right? And are these properties compared to normal tissues? That is my first research question. Second research question or possible outcome can be understanding these technologies can help us to when the surgery is done. This is 1 centimeter tissue that is taken out. We have to also, the surgeon will also be interested in understanding whether this cancer is in the next region. So to do that is you have to immediately check the tissue and when the boundary of the tissue is still cancerous or not. So there is a important area that you have to work on. Research questions again, how different are ETM properties? Do ETM properties change significantly from onset to cancer progression? And can these ETM properties use as an additional markers? We are not here to replace the gold standard. We are here to aid the all pathologists to make a right decision quickly. All right, and of course not to miss TNBC. Chip, you can see here I have shown you earlier also this particular chip, right? If you see the SEM image, which is scanning electron microscopy, the center of this chip, this one where my arrow is, there is a heater. Okay, this 1, 2, and 3, these are thermistors, and this thick line, one here and the second here, these two thick lines that are interdigitated electrodes. All right, now you understand that if I place the tissue between two chips like this, okay, and if I apply a voltage on one side, if I apply a voltage, of course voltage cannot be on one side, voltage is a potential difference across 2 points. If I apply a voltage across this tissue, what I will be able to see, I'll be able to see the change in current. Second thing is, if I heat the tissue from one side of the using a chip, I will be able to see the change in temperature, so thermal conductivity, right? So can I measure electrical properties like change in resistance or change in current and change in thermal conductivity? How can I measure change in thermal conductivity? I'm heating the tissue from one side using the heater in the center, and then I'm measuring the change in the temperature across the tissue using the thermistor that I have here. Now you will see that this thermistor are very, apart from the very far from the actual heater, right? Over here also. But if you see this particular chip, you will understand that the tissue will sit completely on this particular sensing layer, right? So we don't have to worry. So let me show you the system that we have developed. You can see here there is a microchip attachment. There are indenters, there are electronic modules, and this is a complete system that we have developed along with PCBs. The sensor chip is indicated here. It's like a SIM card holder. We don't have to do soldering and wire bonding for this kind of process, right? What is the easiest way to integrate the chip onto a platform? By using a SIM card holder. So this is engineering drawings, right? Like I said, it's a combination of mechanical engineering, combination of electronic systems, combination of microengineering, and a lot of other different domains. So you can see here. Let me play the video. You can see the indenters are going back, right? It's just, yeah, now is reset. Now you play, so it will come towards each other. You have to assume right now that there is a tissue in the center, right? And when it comes close to each other, there is a coarser moment, which is a fast moment, and you can also do a final moment of 10 micron resolution. You see, it's a very small steps. And if the tissue is in the center, if touches the tissue, what will happen is that we can see the change in the properties of the tissue right on the particular UI or GUI. You can change the temperature or the temperature of the micro heater by applying different voltage. You can see here there's a voltage bar, right, and you can see that you can change the voltage across here. So 0.5 volts, 1.5 volts, and so on and so forth. We already know that what voltage, what will be the temperature of the heater, and you heat the tissue now, right, on one side, and you can measure the change on the other side. Once you finish all the things, you can save the data, right, and it will come in the Excel sheet right now. But later on, we don't want to clinician to read the Excel sheet, right? So we will just say a plot, and it is normal or cancer. So this is what we have developed here, right? Let me show you some of the results. You can see that there is a change in the tissue property at a different temperature. You can see here at 4 different subjects, right? You can see that there is a change. Same thing here for tumor, there is a change is significant compared to normal. Same thing for formalin fixed tissues. You can see here the formalin fixed tissues have a significant difference compared to the paraffin embedded blocks. Paraffin embedded blocks is when the tissue is taken out, it is placed in the wax to store for a long time. We got those tissues, we deparaffinized it, removed the wax, and understood the properties of tissues. We also took the formalin fix, the tissue is taken out, immediately placed the formalin, and we tried to use those tissues. Those tissues are much more closer to fresh tissues, and that's why you can see a significant difference between normal and tumor. When we talk about resistivity measurement, we have also done the surface resistivity measurement, where we again see that there is a significant change in the tumor compared to the normal tissues. Okay, so this is one of the topics that I wanted to discuss today, right? We will see the details of other topics later, but let me tell you that what is the translational potential and future prospects of this particular research, right? First is that you can get a free, label-free. Label-free means you don't have to do any secondary biomarkers, right? You have to just have a chip, touch the tissue, you will get the data, label-free. Measurement or diagnostic tool, which is rapid, right, and potentially can be used inside operation theater. It can be deployable in pathology labs and OTs. is an exciting possibility of being applied to other cancer types, where you can see that it can be used for brain cancer, can be used for cervical cancer, can be used for colorectal cancer, can be used for skin cancer or melanoma, can be used for oral cancer. And of course, to get the tissues, we have to get ethical clearance, and the lab should have a biosafety approval. So we got ethical clearance from Assam Medical College, and we have a biosafety approval to use these tissues. So let me stop my discussion for today, or presentation for today, and I'll continue tomorrow to discuss further topics such as understanding the catheter, or understanding the sensors for a brain. It's very interesting because I wanted to show it to you in tomorrow's lecture, that how you can implant the sensor in rat's brain, how it looks like after implantation, whether rat can move or not. Okay, so it's very interesting topics I want to discuss as a part of tomorrow's discussion. So today I'll stop it here, and I'll be very happy to take questions if you have any. Thank you. It will be great if you can ask two questions other than you put in the.
Participants, please ask your questions now. You can post here in chat box.
Oh, I think Savita is asking how sensors are called smart sensors. Okay. Yeah. So you see, smart sensors are sensors that can do something by itself. So until you integrate it with a complete system, right? Sensor cannot be smart. Alone sensor cannot be considered smart sensor until you integrate with an electronic system. Generally, we call smart sensor or sensors of future, or something that can do significantly advanced than what right now sensors are doing. For example, the bioresorbable sensors, right? To implant the sensors, it will give the data for 21 days, and then it will get dissolved in the body. But that's why it's called, like, smartly it is removing itself from the body. That's how we define as smart sensors. So either you understood everything or you understood nothing. If you don't have any questions. You can also prepare a few questions if you want, right? Take your time. I believe, Krishnaveni, I have a lecture tomorrow as well, right?
Yes, sir.
Yeah, okay. So I think participants can prepare the questions if they want. They can ask me tomorrow as well. If they are not prepared right now, they don't have any questions right now.
Okay, sir. Thank you.
Yeah.
Thank you very much, sir, for accepting our invitation. You have explained very nicely about smart sensors and how to use sensors for various applications, sir. And happy to see your lab, sir, and you have shown very informative videos related to breast cancer. Hopefully, participant will ask questions related to that tomorrow, sir. Thank you
Sure.
so much, sir. Thank you so much.
Okay. Thank you all. Bye.
Participants will start the next session at 2:30 as per the schedule. And all of you fill your attendance in the link which is given. And we request all of you to enable your cams now so that we can take a snapshot.
Please unmute your cameras.
Yeah. Thank you, sir. You can unmute. You can mute your cam. No problem. We request all the participants to kindly fill up the attendance link. The link will be closed soon after the session is ended. So we request you all to fill up the attendance in the link which is showed in the chat menu. Again, I am reposting that so that people who have missed it can use it. If you have filled the attendance link, you can disperse for lunch. See you soon at 2:30 p.m. for the afternoon session. Only 34 participants have filled the attendance for the morning session, for session 2, that means the current one. We request everyone to fill it up. People who have already filled it, you can leave the window for lunch and we can join at 2:30. And all the sessions we are recording it. By evening, we will open a YouTube channel and we'll share all the videos in that. You can view it. Kindly join the next session by